Hi everyone, I'm recording Rissa. Thank you so much for stopping by my channel. I love you all so much. Today we are going to be doing a little reading of Why Gravity Matters. And this has been taken from Space, 10 Things You Should Know by Becky Smethurst. I think that's how you say her last name. It's a great book. I'll be putting the title and the author in the description below so you can check it out at your local library or book retailer near you. So let's get into it. I really think this is a great book for bite-sized information on how the universe works, how we discovered that process, the discovery process of learning about the universe, and why it matters so much. So, if you like what you see, please give this a thumbs up and maybe even a subscribe. That would be great. I love making these videos. It's just that if they don't get any likes, I kind of don't feel as encouraged to make them. If you have any cool theories or anything you just want to say, leave them in the comments below and I'll definitely try to reply or give them a heart. So yeah, let's jump into it and let's read Why Gravity Matters. Okay. Why gravity matters. The Sun is just one star in over 100 billion stars in our galaxy, the Milky Way. It's an island of gas, dust, and stars more than 1 million trillion kilometers across. At the center of the Milky Way star system, there is a black hole 4 million times more massive than the Sun. That's something we call a supermassive black hole. And like the sun in our solar system, it's in the gravitational driving seat of our whole galaxy. Isaac Newton discovered the law that governs gravity some centuries ago. Two objects will attract each other proportional to how heavy each object is. The heavier object will apply more force to the smaller object. The force also depends on how far apart the two objects are, so that if you double their distance, the force drops by a quarter. With these laws, we can work out the different effects of gravity between any two objects in the universe, including between you and the earth under your feet. In case you're wondering, you feel a constant force of about 500 to 1,000 newtons, depending on your weight, from the Earth's gravity pulling on your body. For context, the average force of a human bite is about 700 newtons. A great white shark has a force bite of 18,000 newtons. Crazy. All right. The law of gravity brings order from chaos. It is, after all, what produced our solar system. Before the sun formed, there was only a giant cloud of hydrogen and helium gas, with a sprinkling of heavier elements like oxygen, carbon, and iron left over from a previous generation of stars. This cloud was a swirling mess containing the atoms of each element. As each atom is a tiny particle of a certain mass, they were gravitationally attracted to all those other particles in that messy gas cloud. You see my little. Those particles then started to clump together under gravity, with the biggest clumps attracting the other clumps until eventually gravity overcame the energy of all the particles whizzing around and trapped them together to effectively cool them down. The next step was the collapse of the gas cloud down to a really high density where the pressure increased so much that it got hot enough to ignite nuclear fusion. Wow. And our star was born. Nuclear fusion is when stars like the sun turn four atoms of hydrogen into one of helium. And that's why all the stars in our night sky shine. So what was once a swirling cloud of gas full of atoms whizzing around became a burning protostar because of gravity. Now that endless swirling cloud of gas will also have been harboring a remnant of the past. It will have inherited some leftover rotational energy, which we call angular momentum, from a previous generation of stars, perhaps even the first stars to form after the creation of the universe. This means that overall the gas cloud was swirling preferentially in a certain direction, so that the particles started to clump together under gravity. They assumed the same preference. The proto-sun began spinning. What happened to the rest of the gas cloud around the early sun is the same as to what happens to a ball of pizza dough when you spin it above your head. and flattened out into a saucer or a disk, which went on spinning. Inside the disk, the gravitational attraction between particles continued, so that more clumps formed into protoplanets around the sun, giving us our beautifully ordered solar system, where the planets, plus comets, asteroids, and other little bits of leftover rock, all orbit around in the same direction. This process is how we think all stars, not only the sun, have formed. The same thing is reflected down on our own Earth-Moon system. The Earth spins in the same direction as it orbits because the tiny particles that clump together to make it had inherited that hint of angular momentum from the previous generation of stars. Similarly, the Moon orbits around the Earth in the direction that the Earth spins. Gotta love angular momentum. But that's where the similarities stop, because the rest of the Moon's properties are consistently strange. Its day is as long as its year. That means the time it takes to spin around on its axis, its day, is the same time it takes for it to orbit the Earth, its year, which is 28 Earth days. If the Earth followed this example, half of the planet would always be in daylight, and the other half would always be in darkness throughout the whole year, as the Earth made one orbit around the sun. The Earth would spin at the same rate to always keep one side facing away from the sun. This is why we've only ever seen one side of the Moon. We never see its far side because it never points towards us. That's not to say that the far side is the dark side, however, because the Earth doesn't light up the Moon, the sun does. This is why we see phases of the Moon. We see the full moon when it's on the opposite sky to the sun, and which it then fully lights up the side of the moon pointing towards us. And we see a new moon when the moon between us and the sun is so that the sun is lighting up the side that always points away from us. If you're wondering why we don't get a solar eclipse every 28 days, considering the moon passes between the sun and the earth on each of its orbits, the reason is because the moon is not orbiting the same plane as the earth is around the sun. It's slightly tilted by about 5 degrees. So sometimes it passes just below, and sometimes it passes just above the sun in the sky during its new moon phase. All of these properties of the Earth-Moon system might seem like happenstance, but they help us to know something about how our moon is formed. You might expect that the moon formed around the Earth in similar circumstances to how the Earth formed around the sun, i.e. from leftover bits that didn't go into forming the Earth. But our best theory for how that moon formed is a far more dramatic one than that. It's called the giant impact hypothesis, and it says that another protoplanet orbiting the sun collided with a proto-Earth in the early days of the solar system. This impact liquefied the colliding planet and about half of the Earth because of the energy in the impact was so huge. All of this liquefied planet rock was flung out into space while the Earth recovered and kept spinning. But again, that liquefied rock couldn't escape the pull of gravity from Earth, and thus was pulled into a spinning disk that later clumped to form the moon. Wild, right? This theory explains why the axis that the Earth spins around is off kilter. In that collision, the Earth got knocked sideways so that it spins slightly on its side with a tilt of about 23 degrees, like a dog lovingly cocking his head at you. This means that throughout the year, as the Earth orbits the sun, during the southern hemisphere summer, the South Pole faces towards the sun, and 6 months later, the North Pole faces towards the sun. This is what causes our seasons on Earth. It's hotter when our hemisphere happens to be pointing towards the sun due to the Earth's tilt. It's incredible how much order and calmness you can produce out of so much chaos with one simple law of physics. The same law that causes apples to fall out of trees to the ground and keeps our feet on the ground and causes a changing of our seasons affects everything in the galaxy and our solar system. And it's not the only one, and it's not only in our stellar backyard that we see this. Outside of the Milky Way, we even see more of these islands of stars. all shapes and sizes in every direction we look in the universe. Gravity has formed around them huge clouds of chaotic hydrogen gas particles into ordered systems with beautiful spiral structures. But although gravity has made these beautiful islands of stars, it can destroy them too. Most galaxies aren't found in isolation. They are clustered together in groups bound by gravity. Our Milky Way, along with Andromeda, is part of the local group of galaxies. These are the two biggest galaxies in the group, and they are both gravitationally attracted to each other. One day, in the next 4 billion years or so, the Milky Way and the Andromeda will collide with each other, and the gravitational forces between them will tear them both apart, disrupting the orbits of all the stars until everything has settled back down into a giant blob of a remnant galaxy. Milkimedia. Ooh. This is an example of another law of physics, the second law of thermodynamics, which states that the entropy of a system can never decrease over time. Entropy is a measure of how disordered a system is. It looks at how randomly the particles in a system are moving. So the universe as a whole is destined to become more random with the inexorable march of time. In 4 or 5 billion years, our sun will run out of fuel and engulf the solar system, reducing all the stuff in it to one more chaotic cloud of gas. The stars in our Milky Way galaxy will ultimately find themselves on chaotic, random orbits around the center of the galactic blob that will be Milkimedia. Such is the fate of all matter in the entire universe. Even as the laws of physics create order, that order will inevitably descend back into chaos once more. Alright, I want to thank everyone for watching. That was part one, Why Gravity Matters. I really hope you enjoyed it. I will be doing part two, hopefully within the next week. And part two is, in the beginning, there was nothing. So it talks about the creation of the universe and what that looked like, really in depth. If you want to continue this journey with me and this little book club we have going on about the stars, the Milky Way, and space, please give me a subscribe and even a like. Thank you so much again for watching. I love you all. I'm recording, Rissa, and I'm out.